So for this lesson, we're going to be taking a look at extending our treatment of trigonometry to the point where we're talking about the trigonometry of any possible angle. So we're not just going to be talking about the angles you can find in triangles, which would be angles that are between 0 and 180 degrees, but angles that are larger than 180, the idea of negative angles, etc. Now we start with our familiar right-angled triangle. And we use a right-angled triangle. We talk about the sides, the opposite side, the adjacent side, and the hypotenuse with respect to theta. We use the mnemonic SOHCAHTOA to help us remember how those ratios relate to each other. Sine goes with opposite over adjacent, cosine, tangent. To generalize this to any angle, what we need to do, the first thing we need to do is we need to treat our angles as if they are occurring in what's known as standard position. So for whatever angle that you're thinking of, put the vertex of that angle at 0, 0. You may have to do this multiple times for the different angles as you're thinking about it. In practice, we just assume that it's there and it's going to simplify things, but this is the formal process. So if I imagine that the corner of the triangle, so in this case, I'm imagining that that corner of the triangle is at the vertex, is at 0, 0. Is at the origin, sorry, I said vertex, is at the origin. So that's standard position. But that means that I can also describe this point as some other point, xy, and if I draw my right-angled triangle using that point xy, drawing a vertical line and a horizontal line, I end up with the idea of opposite, adjacent, and hypotenuse. And so essentially, I have broken down our regular definitions of opposite, adjacent, and hypotenuse can be thought of in terms of the x-coordinate of a point, the y-coordinate of a point, and r, which is the hypotenuse or the distance between the origin and that point. So that's what we start with as a redefinition or a re-way of thinking about this. So moving on from there, what do we have next? Well, that r value, in terms of actually the reason why it's labeled r is because that r value is the radius of a circle. If I draw a circle from the origin, then r is the radius of the circle. So that's why we're using that particular symbol here. And the value of that symbol, well, we can figure out that r value using the Pythagorean theorem because we can draw a triangle like this. And when we draw that triangle, we end up with r squared equals x squared plus y squared, the Pythagorean relationship. But if we now make use of, once again, SOHCAHTOA, the sine is opposite over hypotenuse, but the opposite side is actually the y-coordinate and the hypotenuse is the r value. The adjacent side to this angle theta is now the x-coordinate and the hypotenuse is the r value. And for tangent, the opposite side is y, the y-coordinate, and the adjacent side is the x-coordinate. So now when I express my trigonometric ratios in terms of sine, cosine, and tangent, instead of writing opposite over hypotenuse, I want to get more into the practice of writing this as y over r, the y-coordinate over the radius of the terminal arm. And because these definitions only refer to x, y, and r, then we should be able to extend these for any possible angle. And we're going to do that now. We're going to go through some very simple examples to illustrate it. One that we actually, this is pretty much what we just started with, but once I construct go through all of these examples, then hopefully you'll start to see how this is more generic. So the 0.43, so I'm not going to worry about scale. I'm just going to roughly try to get things in the right place. So the 0.43, I will draw a terminal arm from the origin to that point. And now for that point, I want to determine the primary trig ratios. Now, the angle is measured from the positive x-axis to the terminal arm in all of these cases. So we're talking about that angle, theta. If your angle is somewhere else, then you have to make use of what you know about things like 90-degree angles and 180, that sort of thing. And we'll talk about that in a little bit more depth as we go along. So in this case, that 4,3, let me just start to break that down just to remind you. So that means that the y value here, the height of this right angle triangle, is 3 units. The x value is equal to 4 units. And then the r value, which is going to be here along the side, the relationship is r squared equals x squared plus y squared. The x value was 4 squared. The y value was 3 squared. That ends up being 16 plus 9. So we end up with r squared equals 25, which means r itself is equal to 5 because, of course, r is a distance and r must be positive. So that r value is equal to 5. Now that I know my x, y, and r, I use my definitions that the sine of theta is now defined as y over r. The cosine of theta is now defined as x over r, and the tangent of theta is now defined as y over x. So sine theta is y over r. That's going to be, in this case, 3 over 5. Cosine theta is x over r, which is 4 over 5. And tan theta is y over x, which is 3 over 4. And the one thing that I want to bring to your attention, notice that all of these results are positive numbers. And that doesn't seem significant now, but as we go forward, keep that result in mind. Okay, the next example, just a small variation, except for now the point is at negative 4, 3. So that means I'm still going to make reference to the positive x-axis here, but I now have to move into the negative, but it's still above the x-axis. So there's the point negative 4, 3. I will, once again, connect my origin to that point. Now, this is something that throws people off the first time they see it. The angle, or they need the reminder of this, the angle is always going to be measured from the positive x-axis. That's what it means to be in standard position. And so I measure that angle. I always measure it, a positive angle is always measured in the counterclockwise direction as well. Now, something that hasn't changed with respect to our triangle is the fact that this r value is still equal to 5. And the reason for that, r squared equals, it's x squared, which is negative 4 all squared, plus y squared. And of course, the negative 4 all squared becomes positive 16 again. So once again, we end up with r squared equals 25, and r itself is equal to 5. So now I have my x, my y, and my r. I have this angle, and as you can see, this angle is over here in quadrant 2, and it's an obtuse angle. It's an angle greater than 90 degrees, but less than 180 degrees. So now we have this obtuse angle, and what do we end up with for our trig ratios? The sine of theta, which is defined as y over r. I'm going to write this one more time. Y over r is going to be 3 over 5. The cosine of theta, which is x over r, is -4/5, and the tangent of theta, which is y over x, is going to be, strictly speaking, that's 3/-4, but we would normally write that as -3/4. Both are mathematically correct. It's just from a communication point of view. And now this is where things maybe start to get interesting in a different way. That's a positive result, but those two are negative results. Whereas when we did this in quadrant 1, in the previous example, when we were working in quadrant 1, all of the results were positive. So now we've moved into quadrant 2, and only sine is positive. The other two are negative. Let's move on, probably not a surprise to you. -4, -3 is a point that's there. We are now in quadrant 3. Once again, I will draw my terminal arm. I'm still going to be referring to the positive x-axis. This is an angle in standard position, which means I measure it counterclockwise. So there's the angle theta. So you can see in this case, the angle theta, if I label that, that's 90 degrees, that's 180 degrees, that's 270 degrees. Well, now I've got this angle theta that's somewhere between 180 degrees and 270 degrees. For what I'm doing right now, I'm not having the angle right on the x and y axes. That's a separate thing to deal with. So the angle theta is between 180 and 270. My r value, just as before, my r value is equal to 5. That part hasn't changed, because even though we've introduced negative values, when you square those, they become positive. We get the same result as before. So now the sine of theta, by definition, is y over r. Well, in this case, there's my x value, there's my y value. So y over r is -3 divided by 5. The cosine of theta is x over r, which is -4 divided by 5. And the tangent of theta is y over x, which is -3 over -4, which actually simplifies to just 3/4. Negative, negative, and positive this time. So once again, only one of the ratios is positive. It's not the same one it was before. It was first, when we were in quadrant 1, all of them were positive. Now that we're in quadrant 2, quadrant 2, sine was positive, and now that we're in quadrant 3, tan is positive. And to finish this up, our visiting each quadrant, the point 4, -3 is about there. I will draw my straight line to the origin. I will put in my angle in standard position. There's my angle theta, 90 degrees, 180 degrees, 270 degrees, and this is interesting. This was the angle we started at, which was 0 degrees, but if we keep going all the way around, that would actually be a full rotation, that's 360. So in this case, the angle theta, which is here in quadrant 4, it's between 270 degrees and 360 degrees. And we could keep going round and round and round and round, generating what are known as coterminal angles, and we still make use of this x, y, and r. Just as before, the r value is still equal to 5. We've kept that constant. That's why I made reference to the idea of a circle, because in exploring this particular set of points, the points as I've explored them have all been points on this particular circle. And I did that just for simplicity. I did that so that I could keep using that R value of 5. So let us now, I think we've got all the information we need to check the sine of theta, which is y over r. The y coordinate in this case is -3, and the r values are always positive, so that's 5. The cosine of theta is x over r, that's 4 over 5. And the tangent of theta is y over x, which is -3 over 4. Sine is negative, cosine is positive, tangent is negative. So what we have is that we have cosine is positive now. So if we take a look, in quadrant 1, everything was positive. In quadrant 2, only sine was positive. In quadrant 3, only tangent was positive. And in quadrant 4, only cosine was positive. So there's a pattern there that we can make use of. And that pattern is the basis of something called the cast rule. The cast rule is just, it's like SOHCAHTOA. It's a mnemonic. It's a little pattern to help us remember. And it's drawn in kind of an odd way, but you do it enough times and you learn this pattern. So we found that when we put our terminal arm in quadrant 1, then all of the ratios were positive, 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 positive. When we put our terminal arm in quadrant 2, only sine was positive. When we put our terminal arm in quadrant 3, only tangent was positive. And when we put our terminal arm in quadrant 4, only cosine was positive. So that's the first thing we want to take away from those 4 examples or exercises that I just did there. The second thing that we're about to build on, and I just want to run through this one last time, let's focus on sine of theta. Sine of theta was equal to 3 over 5. When I moved into quadrant 2, sine of theta was still 3 over 5. In quadrant 3, it was -3 over 5, and in quadrant 4, it was -3 over 5. So other than being positive or negative, all of those had the same ratio. The absolute value or the magnitude was 3 over 5 or 0.6. So what that tells us is that you can have, for example, let's go back and look at quadrant 1 and 2. If I gave you, instead of starting with the points -4, 3, if I told you that the sine of theta was 3 over 5, you actually don't know which angle I'm referring to. Am I referring to this angle in quadrant 1, or am I referring to this angle in quadrant 2? And so that's another element of the idea of trigonometry of any angle, which is that there's a level of ambiguity in this that we need to keep in mind. So one of the skills that we make use of in order to talk about that, I realized I just skipped a slide there. We make use of this idea of the related acute angle. So when we're trying to figure out what our angles are, we have to keep in mind that no matter where I draw my point, for example, here's the point in quadrant 2, here's the angle theta in standard position, I can still always break the problem down into an acute right angle triangle. And I can very easily solve this little triangle, figure out the y coordinate, figure out the x coordinate. Now you have to apply a little bit of common sense, because actually before I say x and y there, how about I say I can figure out, using this right angle triangle, I can figure out the opposite side, and I can figure out the adjacent side, and if necessary, I can figure out the hypotenuse. And then I can apply all of those things back in terms of, well, this is obviously a negative x coordinate, this is a positive y coordinate, and this hypotenuse is positive. This angle, whatever this related acute angle turns out to be, well, that plus theta, for my example that I've got drawn here, theta plus the related acute angle, they have to add up to 180 degrees, because that green line, the x-axis, that's a straight line. That forms 180 degrees. And that kind of rule can be applied to a number of locations. So that being said, let's take a look at another example. Let's try to apply it to some numbers. Express each of the following in terms of the related acute angle, then confirm your answer. In order to do this, the first thing we need to be able to identify is, well, where are these angles? So let me just very quickly sketch this out. Remember, we're always going to be talking about angles from standard position. This is a positive angle, which means I'm going to measure counterclockwise. So there's 0 degrees, 90 degrees, 180, 270. Well, 225 is between 180 and 270. And I don't have to try to get it in the right place. I'm just doing this for visualization purposes. So my angle theta has a terminal arm somewhere here in quadrant 3. The angle theta itself would be there. And so now the question becomes, okay, how can I express this in terms of the related acute angle? Well, if I make a little right angle triangle, then my related acute angle must be there. And so what are so we know theta is equal to 225. And so what's the relationship between theta and between the RAA, and in this case, between the negative x-axis? So in getting to that terminal arm, we had to start here on the positive x-axis, and we had to go that far. So that green arc, that represents 180 degrees. And then the RAA is the little bit of extra we have to go. And those two things total together must be theta, must be 225 degrees. So we end up with 180 degrees, and add the RAA, that must be equal to 225 degrees. So to know what the RAA is on its own, the related acute angle, that's just 225 minus 180. That's equal to 45 degrees. So that's part one. Okay, I've got the RAA. So that means that the sine of 225 degrees must have something to do with the sine of 45 degrees numerically. The only thing I don't know is it going to be positive or negative? And this is where we apply our second part that we just talked about, which is the cast rule. C-A-S-T. And so what quadrant are we in? Here we are in quadrant 3. This is why the order that you draw the cast diagram matters, or the way you remember it. And in quadrant 3, the only trigonometric ratio that's positive is tangent. And that means the other ones must be negative. And so this tells me that sine is negative in quadrant 3, which means that that gets a minus sign in front. The sine of 225 degrees is exactly the same as the sine of 45 degrees. And then in the question it says to confirm your answer. So to do that, we'll just do a quick left side, right side check. So the left side is equal to the sine of 225 degrees. And I've got my calculator here. Make sure your calculators are in degree mode. And then I take the sine of 225. and I end up with negative 0.7071. Negative 0.7071. My right side is equal to the negative sine of 45 degrees, which is negative, and then if I put in the sine of 45 degrees, I get 0.7071. And of course, that negative sign in front just multiplies in, which means that is equal to my left side, and I have verified this. If you're feeling comfortable with that, you could stop here and maybe try that next example on your own. I'm going to work through that now. Once again, just the same as before, draw myself a little diagram. Until you get super comfortable with this stuff, I recommend you follow all the steps that I'm putting in right now. As your comfort level increases, then you can start to do some of this in your head. The angle 160 degrees is in quadrant 2. And so, just draw my terminal arm there. That means the angle itself is there. That is theta equals 160 degrees. And now we look for the related acute angle. Now, I didn't mention this before. The related acute angle is always measured with respect to the x-axis, to the closest x-axis. So in this case, there is my related acute angle. So what's the relationship in this case? In this case, the relationship is that theta plus the related acute angle, so 160 degrees plus whatever this red angle is, has to add up to a total of 180 degrees. And so theta itself was 160 degrees plus the related acute angle is equal to 180 degrees. And this is one of those ones where you might be able to do it in your head, especially when the arithmetic is easy like this. The related acute angle is 20 degrees. So that means that the cosine of 160 degrees must line up with the cosine of 20 degrees, but is it a positive or is it a negative? And so to figure that part out, let's take a look at the cast rule. And in this case, we're in quadrant 2. And in quadrant 2, sine is positive, which means cosine is negative, which means I have to put a minus sign in front there. And then to check that, the left side is equal to the cosine of 160 degrees. And I put that into my calculator. Cosine of 160 degrees, make sure I'm in degree mode, negative 0.9397. Negative 0.9397. And the right side, which is negative cosine of 20 degrees. And of course, the cosine of 20 degrees is positive 0.9397. And so when we apply that minus sign, we end up with left side is equal to right side. And so we've confirmed that relationship. Okay, now in this case, predict the sign of each value, just once again, making use of the idea of the cast rule. So this example is actually easier. I should have done this in the other order. This example is easier than the previous one. The tangent of 135 degrees. I guess you do still need to remember your angles. Which again, you maybe write this out for as long as you need to until you've got it memorized. 135 degrees is over here in quadrant 2. In quadrant 2, sine is the only one that's positive, which means I predict that the tangent of 135 degrees is less than 0. And if I put that into my calculator, it of course is. I'm quite confident in this. Tangent of 135 degrees. It turns out the tangent of 135 degrees is equal to -1, which is a negative number. And CAST. So here we have 240 degrees. Well, that is between 180 degrees and 270 degrees. That is where tangent is positive, which means this one is less than 0 or negative. You could answer these with either a greater than or less than sign, or you could use the words. Now, this one's a little bit more interesting. Sine of 430 degrees. Where is the angle 430? Now, I'm going to take my time here. I start here at 0. I start to build the angle. I make it all the way back to the positive x-axis, and now I'm at 360. And so what is 360 plus 90? That's actually going to be 450 degrees. So that's what's happened is I've actually looped around once and gone a little bit further so that my terminal arm is back in quadrant 1. This is known as a coterminal angle. And in this case, we know that the sine of 430 degrees is going to be positive because they're all positive in quadrant 1. And then finally, we got an example here of a negative angle. Now, the thing that's different about a negative angle is that we measure negative angles in the clockwise direction. So that would be 0 degrees, and that would be negative 90 degrees, and that would be negative 180 degrees, and that would be negative 270, and so on. In this case, we're at negative 30. So there is the terminal arm. There is the angle negative 30 degrees. Which quadrant are we in? C, A, S, T. We are in quadrant 4, where only cosine is positive, which means in this case, the tangent of negative 30 degrees. Remember, this negative is not referring to the angle itself. It's actually telling us that when we evaluate the tangent of negative 30 degrees, we are going to end up with a negative number. And we end up with, I'm just going to double check that, tan of negative 30 is equal to negative 0.5774. Negative 0.5774. That's approximate. And we're almost done, but I've saved the most difficult example for the last because this is where we put everything together. Now I'm giving you the information, first of all, in a slightly different order. I'm telling you that tan of theta is equal to 5 over 24. And I'm telling you that your angle is between 0 and 360 degrees. What quadrant is theta in? And so this is our first, the first twist. I mentioned this earlier in the lesson. What quadrant is theta in? Well, tangent being negative. Where is tangent negative? Tangent is negative in quadrant 1, but it's also negative in quadrant 1, quadrant 2, and in quadrant 4. So it's actually not a single quadrant. Theta is in quadrant 2 or quadrant 4. There's some ambiguity here. We don't actually know. With the information we have, this angle could be in quadrant 2 or in quadrant 4. And I'm going to show you algebraically why that is the case. Now, don't forget the definition, which is that tan theta is defined as y over x. Now, I've got that negative 5 over 24. Hold on, I want to write that very specifically. The ratio is negative. But what could that mean? Well, that could mean that the y value is negative. That could mean that y over x is negative 5 for y and positive 24 for x. Or it could mean that y over x is equal to positive 5 for y and negative 24 for x. So in this case, we end up with x equals 24, y equals -5. And in this case, we end up with x equals -24, y equals +5. And one of these, a positive x coordinate and a negative y coordinate, that's quadrant 4. A negative x coordinate and a positive y coordinate, that's quadrant 2. And that is consistent with our results of the angle having two possible locations. So what does this mean? Well, case 1, in quadrant 2, we said the x coordinate was -24. Actually, before we do that, let's find the r value that goes along with both of these, because it's going to be the same no matter what. R squared equals x squared plus y squared. I can write this as 24 squared plus -5 squared, or I could write it as r squared equals -24 all squared plus +5 squared, because of course they're both going to become positive anyway, and I end up with 24 squared plus 5 squared, and I end up with 601 for r squared. Just going to double check that. Yep. And so my value for r ends up being, and I think I'm going to keep exact values here. So my value for r ends up being just the square root of 601. And that's, of course, because, again, reminder, r is greater than 0. You could write this as a decimal value, but I don't know that there's any particular value in doing that. Usually we're interested in exact values. So that being said, I've got my x, I've got my y, I've got my r. Let's look at quadrant 2. In quadrant 2, the x value was -24. The y value was 5. And of course, the r value is the positive square root of 601. So the sine of theta is equal to y over r. That's 5 over the square root of 601. The cosine of theta is equal to x over r, which is -24 over the square root of 601. The tangent of theta is y over x. We actually already know that. That's -5 over 24. That was given to us in the beginning. You could be asked to rationalize these, or you might see answers in the textbook that are rationalized. So to get rid of the square root in the denominator, we multiply top and bottom by square root 601. We end up with 5 root 601 over 601. We end up with -24 root 601 over 601. And this is the last part. Determine the value or values of theta. Oh, am I done yet? No, I'm not. I'm sorry. That was just quadrant 2. Now we have to do the same thing for quadrant 4. My x value is equal to +24. My y value is equal to -5 this time. My r value stays the same. So sine theta is equal to, in this case, it's going to be -5 over root 601. Cosine theta is going to be equal to 24 over root 601. And the tangent of theta is going to be equal to -5 over 24. So now I've found the ratios for both of those possible angles. Now, how can I use that together to find the value of theta? And sometimes you'll get questions that only do this. Not all questions are going to look for those ratios. Sometimes you'll get a question that will just say, okay, tan theta is equal to -5 over 24. What are the possible values of theta? between 0 and 360 in this case. So I want to show you, let's imagine this was a question just from scratch, just dealing with it right now. I want you to see that you don't have to go through all that other work to answer this one. So what we're going to do is we're actually going to say, we're going to make use of the fact that we know that we can always relate these values in some way to a related acute angle. So let's, in this case, we knew that we ended up with answers that were in quadrant 2 or quadrant 4. Now, where did that come from? That came from the cast rule. Tan is negative, which means it must be in quadrant 2 or quadrant 4. So let's just, for the sake of this particular example, I wouldn't normally do this when I'm solving it, but I want you to see where it's coming from. Let's put our terminal arm, of course I just put it in the wrong place. Let us put our terminal arm in quadrant 2, which means there is one of my possible values of theta. And that would mean that this is the related acute angle. Now, the related acute angle and the angle theta, they correspond to each other. That was the work that we did here. No, it was in this one. The related acute angle and the angle theta, they correspond to each other by all ways they're the same except for possibly a positive or negative sign. So what we're going to do is we're going to say that the tangent of theta must be equal to, it's the same thing as, well, in this case, we've got a negative value because of the cast rule. We know tangent's going to be negative. That's the same as the tangent of the related acute angle. So other than that negative sign, we can relate the angle theta to the related acute angle. Now that lets us do something very important and very interesting, which is, well, if tan theta is negative 5/24, then that means that the tangent of the related acute angle must just be 5/24. Because the related acute angle, it's an angle between 0 and 90 degrees. But this is simple enough now. We can find the related acute angle by taking the inverse tangent of that positive value, not the negative value. This is super important. So I calculate the ratio, 5 divided by 24, and then I take the inverse tangent of that ratio, and I end up with about 11.8 degrees. 11.8 degrees. So that tells me that this angle, this related acute angle, must be 11.8 degrees. So in quadrant 2, my angle theta, how does this related acute angle, what's the overall picture here? Theta, actually before I write my answer directly for theta, I'm going to say that theta plus the related acute angle must add up to 180 degrees. Most people don't write it that way. Most people just very quickly learn to recognize that that's the same thing as saying theta is 180 degrees minus the related acute angle, which in this case, that means theta is approximately 180 degrees minus 11.8 degrees, and that's equal to 168.2 degrees. In quadrant 4, that would put our terminal arm down there. That would make our angle theta look like that. It's going to be the exact same numeric value for the related acute angle, which is 11.8 degrees. You only have to calculate that once. And then our relationship is that, let's see, theta plus the related acute angle must be equal to 360 degrees. And that means that theta on its own must be equal to 360 degrees minus the related acute angle, which means 360 minus 11.8 is 348.2 degrees. So I end up with those two possible answers. So in many ways, certainly this is probably the most common application you'll make of today's lesson. And I tucked it into an example, and taken as a whole, this example has a lot of stuff going on, and you can be asked questions that involve going through this whole thing. But a lot of the time, you're just going to get a question that's like this part C. So this is probably the most important actual skill that's involved in this lesson. And speaking of which, I think that this lesson has certainly gone on more than long enough, and so I'm going to end it right there.